It's a very great honor indeed for me to interview Dana Scott. Dana, of course, is the joint winner with Michael Rabin of the 1976 Turing Award. However, he's accomplished far more than that, having made a wide variety of seminal contributions to mathematical logic, to philosophy, and to other parts of computer science, particularly the denotational semantics of programming languages. What is more, during the course of a long career starting in the 1950s, he has known and interacted with an uncountable number of people, logicians and computer scientists, including those central to the foundations and development of the field. We have clearly much to learn. I am Gordon Plotkin, and this interview is taking place on November the 12th, 2020. Due to the pandemic, it's taking place over Zoom. Dana is in Berkeley, and I am in Edinburgh. Dana, the story is a long one, but luckily there's a standard place to begin with your birth. You have a very long association with Berkeley. I believe you were even born there.
So 1932, October 11, 1932 is my birth date, and it's in Berkeley, California, where I am now in retirement. But my parents were living in San Francisco. In 1932, there were no bridges. The Bay Bridge, the Golden Gate Bridge were yet to be built. So my parents came to a dinner party by automobile using the enormous auto ferries that used to go back and forth across the bay. But during dinner, my mother realized that the baby was imminent, and she refused to go back home on the auto ferry, and I had to be born in the Berkeley Hospital. Fortunately, this hospital is the same hospital that our two grandchildren were born in too, so we have lots of Berkeley connections. My parents were married in Fort Bragg, California, in about 1922. My father was born there. My mother was born in northwestern California near Mount Lassen in Susanville, but then various of the relatives moved to Fort Bragg, and she was living there when she met my father. I wasn't born until about 10 years later, and then my parents were sadly divorced when I was about 5 years old. In our family, I think I was the second to go to college to get a college degree. My father had two brothers and a sister. The eldest brother died tragically in an accident in about 1915, but his other brother came to the Bay Area and after college, became a very prominent dentist. But neither my father nor his sister went to college. And in my mother's family of four siblings that she had, none of them had gone to college, of course, high school degrees, but no college until my time. So my early days were moving around in Northern California in many places. My mother remarried, and we lived on a farm near Susanville, where I started the first grade in a one-room schoolhouse. All the classes were together, and there were just three of us in the first grade. I can still remember it a bit. Then my mother divorced after her second husband turned out had misrepresented his financial position. And I continued school in Reno, Nevada for a year until my mother and I moved to Stockton, California, because other relatives were living in Stockton. There I went to the elementary grades and the beginning of junior high school. I still remember hearing on December 7th, extra, extra, read all about it. Pearl Harbor bombed. I can still hear that sound in my voice. Not long after that, my grandmother passed away. She had a small house in Fort Bragg where she had moved to be near relatives, and my mother inherited it, so we moved to Fort Bragg, where I continued elementary school and the beginning of junior high. My mother remarried a salesman. She was working in sales at the Union Lumber Company department store, and she met her next husband there. And he was located in Chico, California. And so we moved to Chico, where I finished junior high school and started high school. And that was very instrumental in my development because it was a much larger town and a very fine high school there where I attended 2 years. And the key thing there was I had started already in Fort Bragg to learn the clarinet a bit. I'd had piano lessons. Music was very important in my life, all my life. I was very lazy with my piano lessons, and my mother canceled them on me for my laziness. But I took up the clarinet and then continued the clarinet in high school, and the band teacher there was very interested in his students and their development. And he saw one thing about me and giving me lessons and coaching me for the band, uh, being in the marching band, was that I was very interested in why instruments made their sounds. So he had a book that he had acquired many years before by a professor from Case Western called uh, uh, Science of Musical Sounds by Dayton Clarence Miller. He was quite an interesting experimentalist. He had contributed much to trying to determine the speed of light and things like that. And he wrote this book on musical acoustics, which I found fascinating. But the problem with it was it had lots of math, both in calculus and also understanding how it applied to uh, physical physical objects. So I had to learn some calculus on my own. I had a book from my mother, mother's older sister that her husband had had. So I taught myself a little bit of calculus, and I started to understand those things about musical acoustics. After the sophomore year, my stepfather got a new job in Sacramento, and so I was very sad to leave Chico, where I had many friends, and the school was really excellent school there, and the math courses there were quite good. I loved math, but moving to Sacramento was also, it turned out, a great luck for me because it made it much easier to then apply for the University of California. If we had stayed in Chico, I would have gone to Chico State College and become a high school math teacher probably. But going to Sacramento and then having the opportunity to get a scholarship to UC Berkeley really changed my life. But something else changed my intellectual life there in Sacramento. The state of California had a state library, a very dusty state library, and I found there a book on musical acoustics and musical uh, uh, details of musical theory by Hermann von Helmholtz, the famous German scientist. And I was fascinated by that. And the things that I learned from that from the point of view of math was much more about uh, Fourier analysis, of course, not advanced Fourier analysis, but just how musical sounds have overtones and what it means mathematically in understanding those overtones. But the second thing I had to really study, which was hard for me to figure out at first, was logarithms. The reason is that the musical scale is logarithmic. By frequencies, when you advance by an octave, you double the frequency of the sound. But when you count octaves, you only count 1, 2, 3. You don't count the powers of 2. And so I had to learn what logarithms really meant. And then I had to learn what logarithms meant to the 12th root of 2 in order to understand equal temperament, scale, and how you, Helmholtz had very, very detailed studies of different scales and explained the tunings for the different scales in terms of this logarithmic scale. So that I had to learn on myself, and I did a small project for the Westinghouse talent search when I was a senior, and I got an honorable mention for that based on those studies from going back to Helmholtz. But then with the very good teachers in Sacramento, and especially the math teachers were very, very inspiring. I was convinced when I then got the opportunity to go to college that I would immediately major in mathematics. And so that was the result of my high school education ending in summer of 1950. Do you have some questions about what that early history means?
I have a trivial question which I wanted to know the answer to when I actually read your biography. I imagined you as a young person in the dusty state library. How did you find your way there? You just needed more books. You thought, there's a library.
I can't exactly remember. Maybe it's because either through the school library or the city library, it indicated that there were other kinds of books that had been there. I guess they collected them as giving information to the legislators. And so probably no one had checked out Helmholtz for decades, but it happened to be there. So it was a lucky find. And I really love the story of Helmholtz. There's a very fine biography of him. He was a surgeon. He studied all kinds of different things. He was a mathematician. And reading his biography really made me tired because he did so much in his life. And I really feel that I can contribute a lot of my intellectual awakening to some of the writings that he made.
So did that give you an ambition? I mean, you're obviously going to study mathematics, but did you have some view of what your future might be?
No, no, because in high school, you have no idea what college is like. And so I had no thought as, I mean, what had I studied? Algebra and geometry, and a little bit of analytic geometry. And as I say, I had studied somewhat on my own calculus so that I could understand sines and cosines and that kind of thing, behavior of functions. But it was very, very, very elementary. So I had no idea what college was going to be like. But because I had enjoyed mathematics so much, I knew that I was going to major in mathematics at Berkeley.
I can't remember if you said, but was it a teacher who said, "Why don't you go to college?" Or did you think, "I'm going to do that"?
Well, no, I think the high school just encouraged people who did well in high school. The McClatchy Senior High School in Sacramento, California. I think they just encouraged those students to apply to college, and so I did, and was lucky to get a small scholarship to be able to go there.
Right. So moving on to Berkeley, to university, and to what you did there, listen, how did you get to be interested in logic? That's a kind of starting point for you.
Okay, well, partly it was because now I have to remember something. I have a problem these days in my advanced age that I block on words just as I'm about to say them. There was a Polish author, Alfred Korzybski, who wrote about, I cannot remember the name of his famous book, but I had read it in high school,
Oh,
and it had some connection with logic. It was really much more concerned with linguistic understanding. Um, and so I had read about Korzybski. Um, and so when I got to college, the first year there were some courses in the speech department, which I think no longer exists, but there were some nice teachers there, and I discussed some things with them. But then it turned out that in the second semester in philosophy, there was an introductory logic course, very elementary logic, but it was taken as a prerequisite for many other courses. So I signed up for that as a second semester freshman. Uh, uh, Paul Marhenke, who was the teacher of that, was chairman of the department. He was very Germanic in his matter. In those days, people were smoking a lot. He was always covered with cigarette ashes on his vest while lecturing. And it was a nice, easy course. And so I liked logic very much. And then signed up for further logic courses in the sophomore year. The lucky thing is that the teacher the next year was Benson Mates, professor of philosophy at Berkeley, whom I became very, very close to. He had done a thesis on Stoic logic, Greek Stoic logic, but he was very good at lecturing about formal logic. And so his course influenced me a lot. And of course, I heard about Alfred Tarski that way. Tarski was a senior professor in mathematics, and of course a leader in logic worldwide. And so I learned about the possibility of uh, that kind of more advanced work. But the other thing that happened in my sophomore year was that I had signed up for a course called Theory of Equations. Again, it's a kind of introductory algebra course, which is no longer given because it's too regarded as too elementary. The teacher of that course was a young Polish. Uh, he began as a temporary visitor and then got an appointment at Berkeley. He had studied logic in Warsaw. Tarski had left Warsaw for a big philosophy conference in Cambridge, Massachusetts, just at the beginning of the war. and then he was unable to return to Poland. His wife and two young children remained in Poland. She was not Jewish, and she was able to live in the countryside with children. But Tarski was caught here in the States. At first, he had some temporary lecturing in the East Coast, and then he was appointed professor at Berkeley. And so this young person who had studied in the underground university in Warsaw, Jan Kalitzki, had studied Tarski's work very, very closely, had published some small papers. He was able to escape Poland just at the end of the war before the communists took over and went to South America. So he then wrote to Tarski and told him about the work he had been doing, which Tarski liked. So Tarski arranged that he could come as a junior visitor to Berkeley. Then that was about 1951, I guess, when he was able to come to Berkeley. So he was teaching this course in theory of equations, but at the time, in order to help support myself, I was working in the library in the periodicals room. At that time, periodicals had not bankrupted our libraries. There were quite a few periodicals, but not all that many, but they had to be carefully filed because every year they had to be bound up. And so students were hired to do the filing and to keep the things tidy there. So in the periodicals stacks, I discovered the Journal of Symbolic Logic, and I opened it and couldn't understand a thing in any of the articles. I was a sophomore at the time. But there was one paper on truth tables by Jan Kalitzki that I could read because, finite truth tables aren't too hard to understand. And so I was able to read his paper. So when I found in my second semester that he was teaching the course, I then went to him and told him I had read your paper. He was quite amazed and very pleased. And so he suggested that we have more sessions working on those kind of things. And so we became very good friends. And then the thing that was happening with Tarski's approach to logic, he was changing over and had earlier changed somewhat too, from logical systems to model theory. And in particular, he was emphasizing algebraic structures. So rather than truth tables, you should consider an algebraic structure like a Boolean algebra. Boolean algebra defined by equations. There are many, many different kinds of Boolean algebras. So you think of all the models of the equational theory. So the thing that occurred to Kalitzki and me was to think about those equational theories which cannot be extended to have more equations. Of course, you can have a very weak theory which has, for example, rings. Rings needn't be commutative. The commutative law is another equation you could add to ring theory to extend it. But there are also equational theories which are consistent in the sense of having non-trivial models beyond the one-element algebra. But the equational theory cannot be extended further without it collapsing to all equations being derivable. So these we called equational complete theories. So we discovered a number of things about equational theories. Tarski was very interested. He also thought about it in some other uh, aspects. And so several papers, this is during my end of my second half of my sophomore year, several results came forward about equationally complete uh, theories that Kalitsky and I developed. I mean, it's fairly easy stuff in books on abstract algebra now. It's only an exercise, but in any case, that was my first experience in doing any kind of research in the sense of working out things and finding out some new facts. And that, of course, was how I was introduced to Tarski and how he also became a great supporter uh, for me eventually, and of course for Jan Kalitsky. Very tragically, the next year, Kalitsky was killed in an automobile accident. He was a very, very lively person, but he was a terrible driver. He was in the car driving with Tarski, Mrs. Tarski, and one of Tarski's graduate students to go to a American Mathematical Society conference, local conference, and he lost control of the car, which turned over, and he fell out of the car and was killed in the accident. Fortunately, the other people in the car were not injured, but that was a very great blow to me because he was a very warm friend and mentor for me. But by this time, I had been introduced to the Tarski Circle, and so I went on to then in my junior year to really take part in Tarski's teaching, both in courses and in seminars. So that's how I got to logic through the elementary philosophy course, then through Benson Mate's advanced course, and becoming very good friends with him, and then through Kalitsky and introduction to model theory to my introduction to Tarski, and so that's how the beginning started.
Yeah, of course, Tarski was one of the almost founders of logic, of mathematical logic, one might say. So that was an excellent place to be. I was just going to ask what's Tarski like as a person, as a teacher? What was your relationship with him?
Well, he was an absolutely amazing lecturer, as many mathematicians can. He could lecture completely without any notes. So then for the junior year, in Benson Mace's course, I'd met Richard Mague, who was a student of philosophy there and was very close to Benson Mates and came to Mates's lectures. And then a professor from UCLA, Donald Kalish, was coming on a sabbatical to Berkeley, and he was old friend, school friend of Benson Mates. So there was this circle of connections. So we all then, in my third year there, we all went to Tarski's set theory lectures. And of course, they were very, very inspiring because Tarski was a great expositor. And so learning Zermelo-Fraenkel set theory and understanding things like ordinal numbers and all of that. That was quite exciting. So uh, Tarski was uh, a great motivator. He had many graduate students, and so there was quite a big circle of things uh, happening. Tarski also liked to give parties. One thing that he liked very much was making slivovitz. He was able to get people to smuggle pure alcohol in from Mexico, and then he would take prunes or other kinds of things and soak them in alcohol for many months. And then we all had to drink some schnapps at his parties. I remember going to one of the parties, and Ann Davis, one of his early graduate students, came up to me and said, "What are you doing here? You're too young for this." But anyway, there was quite a circle of people and uh, interesting things. Of course, one of the close friends of Tarski were Raphael and Julia Robinson. Uh, Julia did her thesis under Tarski, but was very much aided by her number theory teacher, whom after she had been a student at Berkeley, married there, Raphael. And it was really he that conveyed, uh, you can't imagine the difference between 1950 and today. In the Berkeley Faculty Club, only men were allowed. And so Raphael Robinson was having lunch with Tarski, and Tarski mentioned some things, for example, about after all the work that had been done on first order uh, uh, integer arithmetic, Tarski pointed out that there was many puzzles to be solved about rational arithmetic, the field of rational numbers. And so he suggested certain things to Raphael Robinson, who then suggested that to Julia, and that's how Julia's famous thesis eventually evolved there, where she showed that the undecidability of the theory of rational numbers, and so that was that uh, connection there. And so they were very, very close friends of the Tarski circle. And luckily, one semester they gave a seminar on recursive functions. And so that's really how I learned the basic of recursive function theory from the Robinsons that time.
Oh. So what was one's interactions with Tarski like? Was he like a very severe continental professor, or was it more intimate? I mean, for you, I mean.
Oh no, he was very personable. Uh, uh, I mean, he was very cultured. He uh, well, there were two professors of Polish at Berkeley that he became very, very close to because Tarski had an amazing memory for poetry and could quote all kinds of poetry from memory uh, uh, in Polish. That, of course, didn't do me any good, but he was very interested in cultural things. And he was also uh, 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 very, very open to meeting people and, as I say, having parties and things like that with both students and faculty. And so it was a very lively atmosphere, and he was, of course, very interested in mentoring his students, and of course had many students. That's how I met Saul Fefferman and and I'm blocking on the next name. But anyway, the students around Tarski uh, then were very influential in uh, my further thinking about logic because of the atmosphere that was there. That Tarski certainly uh, created the atmosphere that was very congenial.
Right. So coming back to Richard Montague, what did you work with him? Were you just like students talking about everything together?
It was more like that. So he then became Tarski's graduate student and did his thesis under Tarski, but it was just learning about logic. And so, for example, for the set theory course where there was Montague and Mates and uh, again, I'm blocking on the name, other people. What we had to do afterwards was to, after Tarski's lectures, we had to do the homework. And so there was a group of us who got together to discuss all the homework problems and to work out the proofs and that. And so that was my first uh, my first interchanges with Richard. Later on, we became very good friends and roomed together just before he was finishing his thesis. And then, luckily, Don Kalish, who had come to Berkeley and went back to UCLA, hired Richard Montague to come to UCLA just in the last year before he finished his thesis. And so he eventually then became a full faculty member at UCLA there. And so I visited UCLA over the years many times. And the people there was another circle of people interested in logic too. And so that was part of the connection. I suppose Richard and I were somewhat, in some ways, rivals, especially rivals to get Tarski's uh, attention and that sort of thing. And so there are some stories of things that are said to Richard that may be a little bit insulting, but it doesn't matter anymore in any case. It was a very lively intellectual atmosphere and created lots of intellectual activity, of course, very much based on Tarski's deep influence.
That sounds wonderful. I want to ask a question, since I have the opportunity to ask you questions. It's not so much about you, but Richard went on to invent the denotational semantics of natural language. Did you ever talk to him about that, or do you know how that came about?
Well, what we discussed together, and I also wrote about over several years, was modal logic. One of the things that happened in my undergraduate year was that I found the early book on modal logic, and of course I'm blocking on the name of Lewis and Langford on modal logic. And so already as an undergraduate, I'd studied Lewis and Langford. And of course, modal logic interested Benson Mates and Richard Montague too. Tarski, of course, with some of his earlier students, had done a lot about modal logic because he thought of it as an extension of Boolean algebra with Boolean algebra with operators. And so there are those papers. And so I also studied Tarski's papers on algebra of operators very much. And of course, that led to other things much later in thinking about kinds of Boolean algebras with additional structure. And so that was a connection that came up between me and Montague about modal logic and what you could do with modal logic. And of course, in thinking about natural language, modalities are very important. And so, of course, that figured very heavily in Montague's thinking as well.
Oh, that's a fascinating connection. Circling around, you already mentioned Saul Fefferman. another wonderful addition. Can you say anything about how Saul was then, and how was he just part of the group there? I mean, he would at least be part of the group.
Yes, he and Bob Vaught were the two senior graduate students. Oh, there was also C.C. Chang, also at the same time. Vaught and Fefferman worked together, and they were very influenced by Tarski's theory of models. But of course, eventually, Fefferman moved over to proof theory. Tarski never lectured about or encouraged anyone else to lecture about proof theory. I chided him on that once, but it really didn't interest him so much. But then, coming from the Tarski school, then Saul Fefferman became the leader of thinkers about proof theory, and had a big influence and many connections there. But before, um, maybe it was during my senior year, Fefferman was drafted, and he and his wife had to leave for him to take up his military service, which he served in the East Coast, somewhere not overseas. And so that was, he was pulled out of the circle by having to uh, be drafted. This was, I guess, during the Korean War.
Really?
And Vaught remained there and was very much an inspiration in his work. But it was only later, after Fefferman had his professorship at Stanford, that I had then closer connections with him and his family through Stanford. But that's a later period.
Yes. I was wondering, did you want to say anything else about any of the other graduate students then? That you mentioned several names. I don't know if you want to say any more.
Well, Anne Morell, who was at that time Ann Davis from her first marriage, and then her later marriage was Anne Morell. She had already left Berkeley, but came back to visit many times during the early 50s there. And so I got to know her very well. And then Tarski had a student, Tom Frayne. What happened was that in the later 1950s, as the connection with the 1957 NSF Summer School on Logic, 6-week Summer School on Logic, which was the first big meeting of logicians in the United States. Tarski raised various questions about how you could use products to show that certain theories were consistent. And that suggestion that he made during that 1957 meeting then led in various ways for Anne Morell, Frayne, and myself, somewhat independently, but then jointly with them, to develop ultra products. But that was a much later development. We're still talking about my undergraduate years at Berkeley, but that happened then in my end of my graduate work there, but keeping connections with the people in Berkeley, and as I say, particularly Morell and Frayne.
That's very interesting to know that. Hey, so you became a graduate student of Tarski, but that didn't last. There's a story. I don't know if you wish to tell it.
Well, I'm not going to tell too much about it, but Tarski had many of his early writings translated into English. They were in German mostly, translated into English by J.H. Woodger, the famous biologist who was very interested also in logic. And a big volume was in preparation, in which Tarski was getting the page proofs. But the translations were not satisfactory to Tarski because, of course, Woodger, even though through best intentions, but as an amateur, didn't understand the logic completely there. And so the page proofs had to be corrected. And so various of us were helping Tarski collect the page proofs, and Tarski actually hired me as a secretary to do those things. Reading the page proofs was a horribly boring job, and I got very lazy about it. And because of my laziness, Tarski became very angry, and finally at one point had to fire me because I wasn't doing the work that he was paying me for doing. So that was our break there. Just at that point, this was this was in my first graduate year after graduation in 1954. I graduated in 1954 and became a graduate student at Berkeley the next year under Tarski. But Norman Steenrod was visiting on a sabbatical from Princeton, and one of the other professors, finding out about the difficulties that I was having, of course, it was entirely my fault, the difficulties, saying, well, why don't you think of going somewhere else? Steenrod is here, go and interview him. This was from Harley Flanders, the algebraist that I took his course in advanced algebra, suggested that I do. And because I'd already had some independent research on my own, Steenrod was very interested to meet me and said, of course, you should apply to Princeton, and I'll be glad to write a letter of recommendation for you. And so that was that connection with Norman Steenrod being there on sabbatical, and that was then the connection to apply to Princeton for graduate school, and that's where I went the subsequent year.
Yeah. Before we go on to Princeton, maybe one final summary question about Tarski. How would you speak of what he meant to you, what his position was in your life?
Well, I think it was his intellect. I mean, the studies of logic and foundations and set theory and axiomatics and that sort of things really grabbed me. But he was an absolute superb expositor to make things understandable and to formulate things in a clear and simple way. I mean, he was really outstanding talent at that. And so that was how the influence really settled on me. It was his intellectual powers of being able to explain things, and I think that's what I credit him for. Of course, he also was very productive, and proved so many things. And of course, we all studied things about the undecidability. The Robinsons were very much concerned with undecidability questions, and Tarski, Mostovsky, and Robinson wrote their monograph on undecidable theories together. And so also that kind of exposition was very influential also on my learning things. Let's go back to my sophomore year at college.
Okay.
I was learning about formal theories, and I found the little book by Paul C. Rosenblum on mathematical logic, which covered many topics. One of them was Zermelo-Fraenkel set theory. So I learned quite a bit on my own reading Rosenblum's book on set theory. But another chapter of the Rosenblum book was combinators and lambda calculus, Curry's combinators and Church's lambda calculus. At the same time, I also got a copy of the very small volume on lambda calculus that Church wrote as well. And so I studied those things in my sophomore year by those books. Now, in the Rosenblum book, he explains in a fairly short order the complex interrelations between Curry's combinators. And so I like to say that one afternoon, after spending a lot of time trying to puzzle out how combinators combine and what they do to reproduce one another through their equations, I worked so much on it that at night when I went to bed, I had nightmares about combinators. There were all of a sudden these gigantic combinators that were coming to bite me or to do something terrible. And I don't know whether that nightmare about combinators was what cemented my interest in thinking about lambda calculus, but that's exactly how it started. But I didn't do much else about combinatorial logic or lambda calculus in the early years at Berkeley. When I got to Princeton, I was very interested to meet and be directed by Alonzo Church. But unfortunately, because Church had originally thought that he had solved the logical paradoxes, and his logistic system, which involved lambda calculus, was going to solve the problems that Frege couldn't solve that led to the Russell paradox. But unfortunately, Church's two students showed that his system of logistic was inconsistent. The only thing that was left, so to speak, of it was the equational part of lambda calculus. So Church wrote that up in his small monograph, but the logistic system that he had such hopes for failed. So much later, when his monograph was published in 1940. Much later, when I got to Princeton in the late 50s, Church never discussed lambda calculus with his students. He did, of course, somewhat earlier write about typed lambda calculus in his formulation of the theory of types that many people pursued, and particularly his student Leon Henkin very much worked on Church's theory of types. But the untyped lambda calculus, Church never lectured about and never discussed with any of his students. And so it's really too bad. I never had really a chance in order to discuss modeling untyped lambda calculus in later years.
Yes. Well, but did you think about models of lambda calculus even then, or the thought that there could be?
No, not really. I mean, I, of course, understood it as an axiomatic theory, but not from any model theoretic point of view. Of course, the typed lambda calculus had all kinds of models to consider that many people worked on, but the untyped lambda calculus, I didn't at all think about it from a model theoretic point of view at that time. We're talking about the late 50s.
Right, right. So jumping a tiny bit, Turing was a famous PhD student of Church, obviously a large number of years before you arrived there. Did Church ever say anything about Turing or how all that went? Or
No, he never spoke about Turing. Even with the Turing centenary, Church wrote uh, only very little about him. I don't think there was a close personal connection. Turing didn't like being in the States very much. He was only there for 2 years. He had really been recommended to go there because of the Turing machine approach to undecidability that he had developed as a student in Cambridge. And he was mentored by von Neumann, who was professor at the Princeton Institute for Advanced Study. But Church insisted that he formulate all of his work in terms of lambda calculus. And in one of his letters, Turing said how much he hated to do that, but it was what he did in order to finish his PhD under Church for using lambda calculus for transfinite computation. But I don't think they had a personal, very much personal relationship.
How was your relationship with Church? Was he helpful for your thesis, or how was it?
Not really. Church invented the reviews for the Journal of Symbolic Logic, which had started in the middle 30s. And he spent a Herculean amount of effort on promoting the reviews. And even at the time that I was at Princeton as a graduate student, he was spending most of his time editing the reviews. And so it really didn't relate in much connection there. I was there only for 3 years. Of course, he had several graduate students, including Michael Rabin, that we'll want to speak about. But he would, his kind of direction was to discuss with the students what kind of area of research that they wanted to do, and then he just let them do it. I very unkindly like to say that Church corrected the spelling in my thesis, but the problems really came from Tarski much earlier, and so he didn't have really much influence on my research topics at all.
Okay. A slight side excursion, and noted that you, with Hale Trotter, you worked on the Princeton von Neumann machine, or you worked with it. So you did some programming. Can you tell us about that? Perhaps escapade, I don't know if that's the right word.
Yes, that was, I mean, we're jumping ahead here, but that was very late in my time at Princeton. I had become friends with a professor in electrical engineering called Foreman Acton, who was an early advocate of computing machines. And it turned out that he had money for a summer project. This was in my senior year for working on using the von Neumann machine. You see, the von Neumann machine is very well written up by George Dyson about the history of von Neumann and computing at the Institute for Advanced Study and the development, which was a great engineering feat to develop the von Neumann machine there. The von Neumann machine eventually became the basic blueprint for the IBM 707 series, was taken over. And of course, there was one version of it at Los Alamos. But after von Neumann died of cancer, I never got a chance to meet him. He was already ill in the hospital when I got to Princeton. The Institute for Advanced Study never wanted to have anything to do with engineering, and so they gave the von Neumann machine to Princeton University. There were several people still using it for astronomy and other kinds of calculations, but it was given to the university from the Institute for Advanced Study. Unfortunately, the university discovered it's very expensive to keep a machine like that running. For example, the memory of the von Neumann machine was electrostatic tubes, Williams tubes. By exciting an area of the phosphorus on a tube, the excitement would persist for a small interval. And so that became a memory because you could keep refreshing the excitement, and that's how you preserve the memory. And so there were only 1024 words in the memory, and it was very tricky to keep it running well. In fact, the electrostatic tubes were much affected by humidity. Princeton can be very humid. So the best time to work on the von Neumann machine was 3 o'clock in the morning on account of its physical characteristics. But Foreman Acton hired Trotter and myself to do some projects on the von Neumann machine because the university had just had been able to get access to it. So Trotter and I thought it would be a good idea to work on some kind of combinatorial problem, and the influence on doing the work on it had really come from the popularity of a puzzle called pentominoes, which was a kind of jigsaw puzzle with different shapes made out of squares, and you have to fit them together to make a rectangle. And so we thought that would be easy to code up in terms of binary numbers to search for solutions to this jigsaw puzzle thing. And so that's how we, because of the interest that many people had had in the puzzle, the Robinsons, for example, in Berkeley, loved puzzles, and I think they had introduced me to pentominoes in the first place. But all kinds of people, including Martin Gardner, liked it very, very much. And so the interest in this kind of combinatorial puzzle was in the air. But then it was the close friends of the Robinsons. Oh, again, I'm blocking on a name. I'll think of it in a minute. They had done a lot of number theory computation on the SWAC computer at UCLA. And in doing searches, they had done, I'd heard them lecture on the backtracking method, which means you follow some conditions forward until you reach a brick wall, and then you backtrack and change one of the conditions to branch off another way. And you keep backtracking and backtracking until you find the path to a solution, or eventually even to all the possible solutions. And so the Lamers, it was Dick Lamer, the professor of number theory at Berkeley, who was close. He and Emma Lamer, his wife, were close friends of the Robinsons. That was the inspiration for understanding backtracking. And so that's what was applied in doing the combinatorial puzzle on the von Neumann machine. And it worked out. We were able to completely do one version of the puzzle. And that was the summer of '58. And then I think by the fall, the uh, the Institute for Advanced Study had closed down the von Neumann computer. Eventually, I saw the corpse of the machine, which was very sad, in the Smithsonian Institute, because what was fun about the von Neumann computer, because it had these flashing lights on the cathode ray tubes to check the memory. After you did your programming on punch cards and it was read in, you then could watch the progress of your computation by watching the flashing lights on the cathode ray tubes. And it was so sad to see the guts of the von Neumann machine as a dead corpse displayed in the Smithsonian Institute. But I strongly recommend reading George Dyson's book called Turing's Cathedral, which he gives a complete history of the von Neumann machine and the many things that were done with it. But that was my small connection with it through that summer job. Okay.
Yes, indeed. Yeah, and I agree. That's a very nice book by George Dyson. But so many questions one can ask. In connection with the Institute of Advanced Studies, of course, Gödel was a famous member. Did you already meet Gödel then? What was your interaction then, if you did?
I didn't become close to Gödel really until I was a faculty member at Princeton in the early '70s. When I was a graduate student in Princeton, Church introduced the students to, or Gödel to Church's students, and there were interactions there. But during my time as a graduate student there, I became very closely associated with a visitor, Georg Kreisel, who came to the Institute for Advanced Study. He and Gödel were very, very close. Kreisel and Gödel loved to talk for hours on the telephone. Both of them were very hypochondriac, and talking on the telephone is an excellent way of not spreading any germs. And so they would have hours-long conversations on the telephone, of course, in German. German was a very important thing. I'm sure that the German language was one of the strongest things that made his friendship, Gödel's friendship with Einstein, because both of them felt somewhat culturally isolated, and so being able to talk to each other in German was very important for them, as it was with Kreisel and Gödel. And so I learned a lot about Gödel's thinking through Kreisel. And I feel I should go over some thoughts about that, and we'll have that details of that as the topic of conversation in our next session. But for the time being, when I became closer to Gödel, and he was, of course, could be very gracious, and he wrote once a nice letter about work I did about set theory, but that really transpired in the later time, in the early '70s, when I was a faculty member at Princeton. Let me say something more about Princeton. Of course, it was a very exciting atmosphere because so many mathematicians and people visited Princeton. And of course, that was how I met Kleene. Kleene was one of Church's earliest students, second or third student, along with Barclay Rosser. They came to Princeton often to visit, but Kleene came for a sabbatical year while Church was on leave. And so I became close to Kleene at that time, and that was very inspiring. Many, many other visitors came for talks and seminars, and many famous mathematicians. Of course, Emil Artin, of course, I knew about some of Artin's work in algebra because Tarski discussed real closed fields, and the Artin-Schreier paper on real closed fields was very important. And so it was quite exciting to meet and hear Artin lecture, but there were many other very interesting mathematicians at Princeton. And so it was a big, together with the Institute for Advanced Study and all the visitors who came there, it was a big influence on me to see that wide culture of mathematical research. And so it was accidental in a certain way that I went to Princeton, just like it was accidental that I went to high school in Sacramento. Those accidents were enormously helpful in the long run.